Okay, welcome to the Chapter 6 Trend Notes. If you have been absent or if your teacher is absent, this is how we're hoping to get these notes to you in a way that you don't have quite as many questions as if you had been in class with your teacher doing it together. So find this page in your notes packet, Chapter 6 Trend Notes, just after the assessment questions for Chapter 6. And we're going to start with some common definitions. So first off, valence electrons. Hopefully you remember that we can abbreviate valence electrons as VE negative. Okay, and we're going to go through and just define them again. These are the highest energy electrons in an atom, and these will always be in S and P orbitals. The highest energy electrons in an atom, which will always be in S and P orbitals. So if you remember the D block, when you get to the Ds, they're one energy level lower than the row number that they're in. So they'll never be your highest energy level. S's and P's are always going to be the highest energy level for an atom. Okay, next we have atomic radius. Okay, atomic radius. In the book they define it as half the distance between two atoms of the same element that are bonded to each other. That is how we find atomic radius. But when we're talking about a radius of a circle, we're talking about from the center to the outside of the circle. So we're going to keep that the same thing here. For an atom, the center is the nucleus. So your atomic radius would be the distance from the nucleus to the valence electrons. Okay, those outermost electrons in the atom. Okay, and atomic radius is used to compare sizes of atoms. Used to compare sizes of atoms. So if we're talking about a bigger atom or a smaller atom, we just mean it has a bigger or a smaller atomic radius. Okay, next, ionic radius. Okay, it's the same definition as atomic radius, but instead of an atom, we're talking about an ion. And remember, an ion is when it has either gained or lost electrons, and now it has a charge, either positive or negative. And so, same definition, but with the word ion. The distance from the nucleus to the valence electrons of an ion. Okay, used to compare sizes of ions. Alright, ionization energy. Okay, this one pretty straightforward in the book. It is the energy required to remove an electron. Energy required to remove an electron from an atom. Okay, energy required to remove an electron from an atom. Okay, and then finally, in our definitions here, we have electronegativity. Okay, electronegativity is the ability of an atom to attract electrons while in a compound. Okay, so the only elements that do not have an electronegativity are going to be the noble gases because of this last piece, while in a compound. Noble gases don't form compounds, not readily anyway, and so we don't have a way to measure their ability to attract electrons while in a compound because they don't form compounds. Okay. All right. Now, with those definitions, keep them in your mind, keep referring back to them. We're going to go ahead and talk about what happens to atoms as we go down a group or across a period in the periodic table. And again, this is based on atomic structure, which we learned in chapters 4 and 5. So let's just start off the bat with nuclear charge. Okay, nuclear charge. If you remember, the atomic number up here in the upper left corner of our planes and periodic table, that tells you the number of protons and also the number of electrons. Hopefully you remember that the protons are the piece of the nucleus that has a charge. Okay, so nuclear charge is all about number of protons. And this might not be legible to you, but if you were looking at your planes and periodic table, as you go down a group, that number is getting significantly larger as you move down that group. Okay, so if we are talking about nuclear charge, as you move down a group, what happens? Okay, well, there are more protons in the nucleus, which makes it more attractive, which makes the nucleus more attractive for the negative electrons. Okay, so as you move down a group, there are more protons in the nucleus, which makes the nucleus more attractive for the negative electrons. Okay, opposites attract. So more positive in the middle means more attraction for those negative electrons. Okay. All right, electron shielding. Now I really want you to think of this as layers of electrons in the atom. Okay. Every energy level represents a different layer of electrons. Okay, they're in their orbitals, but they're also at different distances from the nucleus. Okay, energy level 1 is the closest to the nucleus, least energy. And as you move out, away from the nucleus, you're getting more and more energy. So again, if we go back to our periodic table, as we move down a group, we're getting lots more energy levels here. Every time you move down a row, that's another energy level in the atom. So from helium to neon to argon, we're going 1 to 2 to 3 energy levels, etc. as you move down the periodic table. Okay, so as you move down a group, the number of energy levels increases. Okay. Again, those are electron layers. Number of energy levels increases, electron layers, which shield the nucleus from attracting the outermost electrons. Okay, the number of energy levels increases, or electron layers increases, which shield the nucleus from attracting the outermost electrons as strongly. Okay. So we have one change here. There's more protons in the nucleus as you move down a group, which should increase the attraction towards those negative electrons. But we get more layers, and those layers are blocking the outer electrons from seeing the nucleus as well, okay, or experiencing the effect of the nucleus as well. And so which one do you think has a greater effect on the attraction of those electrons? And you might not have any idea here, but let's just go ahead and talk about it, okay? The one that has the greater effect is the shielding. Okay? So shielding increases have a greater effect. Okay? What this means is we have a weakened nuclear force, weakened force between the nucleus and the valence electrons. So yes, we're getting more protons, which should mean more attraction to the electrons. And it is, but because there's more layers in between the valence electrons and the nucleus, those are blocking that pull. And so what we end up having is a weakened force between the nucleus and the valence electrons. So those valence electrons, as you move down a group, the valence electrons aren't quite as strongly attracted to their nucleus in, for example, argon as they are in neon. The valence electrons are closer to the nucleus. They don't have as much blocking that positive pull from the nucleus in neon as they do in argon. An extra layer blocking that pull from the nucleus means that the valence electrons aren't quite as strongly attracted to the nucleus in argon as they are in neon. Now let's talk about that same concept, but as we move across a period. Okay? If you look at the periodic table, the atomic numbers as you move across a period are also increasing. So there are more protons in the nucleus, which makes the nucleus more attractive for the negative electrons. So we just wrote exactly the same thing here as we did up here, because as you move down a group or as you move across a period, okay, and across a period means left to right. If you want to add that for yourself, you can, okay. In English, that's what it always means, but we'll just go ahead and write that there. Left to right, there's more protons in the nucleus, meaning the nucleus is more attractive for the negative electrons. But now let's look at that in terms of shielding. If I'm going from sodium to magnesium to aluminum, silicon, phosphorus, sulfur, chlorine, argon, I am in the same row of the periodic table, which means I'm in energy level 3 in this case, because I'm in the third row, the whole time. There's not any difference in the number of layers between sodium and argon. They all have 3 layers. So when we go back over here, our shielding is actually constant. Okay? Atoms contain the same number of energy levels, or electron layers. So the amount of shielding between the nucleus and the outer electrons remains constant. So again, atoms contain the same number of energy levels or electron layers as you move across a period. So the amount of shielding between the nucleus and the outer electrons remains constant. So if we're looking at those two changes, well, really we only have one change. We're increasing the number of protons as you move across the period, but they're not gaining any more shielding, any more layers. So the increase in protons is really the only change. Okay? The increase in protons with no change in electron shielding is going to equal or result in a stronger force between the nucleus and the valence electrons. Okay? The increase in protons with no change in electron shielding is a stronger force between the nucleus and the valence electrons. So if we go back to our periodic table, as you're moving down a group, you're getting more protons, but you're getting more layers, and those layers block that nuclear pole, and so we end up with a weaker nuclear pole as you move further down the group. And then as we go across, we have the opposite effect. More protons, constant shielding. The more protons is the only change that causes an increase in attraction as you move across the period. So argon has a stronger attraction to its valence electrons than sodium does, because more protons. But argon has a weaker attraction than helium because there's layers blocking that attraction between the nucleus and the valence electron in argon. Okay? Alright, so we'll go ahead and say that's the end of the first page, and we'll go ahead and watch another video to cover the second page of the notes. So keep these changes in mind, and we're going to flip or turn to the next page and talk about what happens there.